Technique, yeah. Hi, everyone. Thank you for your patience as we were figuring a few things out with the technology. Welcome to Silo Seminar. It is my pleasure to introduce Professor Alon Orlitsky. He's visiting us from San Diego. He's a professor in electrical and computer engineering and computer science and engineering at UCSD, and also Qualcomm Chair for Information Theory and Applications. So Alon has a really long list of accolades. He and his students have worked on problems that have won many best paper awards in several different conferences, and as well as for in information theory society paper award and so on. So given the time, I will hand it over to Alon so that he can tell us more about some of the exciting works he's been doing on LLMs recently.
Okay, thanks a lot, Ramya, and thanks everyone. Thanks for inviting me and organizing this meeting. And sorry about the starting delay. And so I think in the meantime, you saw my jokes, so maybe we can skip them. Like there was a joke when I was going to give the talk, yesterday, and there was going to be a public announcement which tells you there was tax day and you should pay your dues, but not during the talk. And now there's another quote unquote joke that I didn't do right, that it wasn't 15 but 16. Okay, and then there'll be a couple. I was working on the slides, so there'll be a few slides that are not completely well done. But so this work is about improving the perplexity of English by modifying LLMs, and it's joint work with my student Esen Ergun, who's shown here, who's done a lot of work. What I'll show you is only some of what he's done about this. Okay, all right, and the purpose is basically to show you, or to try and argue, that information theory has something to say about LLMs, and with even doing like some simple stuff, we can possibly improve things. That's the goal. So okay, so maybe we can start with a brief history of information theory. Essentially started in 1948 with Claude Shannon, and he wrote a Bell Labs technical memorandum that ended up changing the world. It was called a mathematical theory of communications, and in this article, he introduced a very simple concept called entropy that measures the random distribution, and the formula I think many of us are familiar with. And he used it to show two important applications of entropy. One is compression, which is minimizing the number of bits that you need to represent random phenomena. And the other one is communication, where he used, again, entropy to find the maximum number of bits that you can convey over a channel when you can communicate, okay? But since this entropy, as we see, is a measure for just want to see if you can see the cursor. Oh, I cannot see it. Right. Okay, maybe what was this? Okay, we cannot see the cursor, right?
Check. Yeah, if you want to like go closer to the.
Okay, but then this does not change the slides, so that's the other issue. No worries. Okay, so entropy. So stay here. Okay, so entropy is, as we said, a measure of the randomness, and so subsequently after 48, people use this measure to first evaluate. And once you can evaluate things, you can improve many applications, many different tasks. Okay, so this is 1948, and then just with like maybe 1956. So 8 years, just 8 years later, there are many applications, and Shannon wrote another article. It's called The Bandwagon. Okay, and in it he mentioned all the applications that. Not all, we mentioned some of their many applications, and actually one of them I should have definitely mentioned here is linguistics, that people have used it and said, oh, it's good that information theory helps with these things, but let's be focused on things and try to be more mathematical about them and more systematic and so on. It's not just do it. Okay, so that was this is 1956, and then fast forward 70 years. Okay, and here is information theory, and there's a new game in town. Okay, it's ahead of information theory AI, which has many applications, and basically very often it's generative AI, where you generate, let's say, text or images. Okay, and it's used for many applications. Used to answer questions, create conversations, used to create programs, to summarize things, to help with reading things, and so on. And basically, it consists of two phases. First one is pre-training, and then fine-tuning, and that I'm going to quickly describe now. So pre-training, so you have a language model, which typically is a model for next word, just predicts the next words given the past, and you have many such models that have been pre-trained. Maybe we don't need to go over all of them, but they have like many parameters, like trillions of parameters. So these are the ones, the private ones, and then the open source that still have many parameters, and then they're trained on very large corpus, basically anything that one can see, including large like corpora, like common crawl and the pile and so on. And so when you want to apply to a specific application, then what you do is maybe you retrain on the relevant database, for example, Stack Overflow and so on. And maybe you can skip this. So when you look at the pre-training, like you look at the costs. So a couple of years ago, Forbes magazine published an article about how much it costs to train such a model, and these numbers are in millions, in millions, and you can see that to train like Gemini 1 would cost you about almost 200 million, and even if you amortize over like what Google already has, then it costs like maybe 40 million to train such a model, and that's excluding like that's just for the train itself, including the cost of labor and so on, which would add about let's say 30 to 40%. Something like that. So it's very expensive, not something we can do. And so then comes the fine-tuning part, which was the second part. And so while we gain most of the knowledge in the pre-training, that is extremely expensive, the fine-tuning, what you do is you tailor the model for specific tasks, for example, for questions and answers and so on. So you do something, you modify the basic model for specific applications. And when you do that, then the cost is somewhat lower. So maybe somewhere between $500,000 and $1 million. So a lot less expensive, but still for most of us, not for wealthy UW faculty, but for the rest of us, it's pretty expensive. So what I'd like to talk about today is how we can try to improve things, not just with pre-training or fine-tuning, but with post-processing, the cost of which should be about that of buying it like the Mac that I'm using. So just use like a Mac and do some post-processing and still improve on state-of-the-art results. Okay, so that's the goal. So what we do is, what we'll talk about is this. We'll talk about using existing models, and then what we'll do is we just modify or add a few parameters, and that's one approach. Another approach we'll take different models and combine them and improve the state-of-the-art on important benchmark that will show. Okay, cool. Okay, so now the way these systems are trained is using something called perplexity. And I've talked to a few people, and I get the impression that not everyone is familiar with perplexity. So let's just go over what it is. So you have trained a language model, call it Q. It's just So what Q is basically an estimator that if you give it a sequence of words, W1 up to Wn, then it will calculate the probability. It's the probability of that it estimates using all the training data, the probability of the ith word given the previous I minus one words. And so what we see, it's just a product of n probability estimates, okay? And the perplexity is just the nth root of 1 over this probability. Okay, so if we just plug this in, it's the nth root of the product of 1 over q wi given wi minus 1. Okay. I'm hoping this is completely clear. So if not, you can ask questions, but the goal is to make sure that it's completely clear. So it's this product, and what we see is that it's just the geometric average of 1 over q of wi given wi minus 1, right? And for between 1 and n. So, for example, if we say that Q, if we see the word Abraham, and then we look at the following word being Lincoln, so maybe it will tell us that the probability of Lincoln following Abraham is 1 over 8. And what's the meaning of that? That means that it thinks that that Lincoln is one of 8 possible words, equally likely words that can follow Abraham. Okay, so Lincoln is one of roughly 8 words that are likely to follow Abram. Okay, and so what the perplexity is just like the geometric average. Maybe we don't worry about the geometric, but it's the average number of predicted words following each context. That's what perplexity is. So if the if the perplexity goes down, that means that have a better estimate for the subsequent word. Okay, so that's a better language model, and so the quality of the language model increases, and that's good. And if we have perplexity 1, that means that after every word, I somehow predict exactly what's the next word. Of course, impossible, but that's what perplexity 1 would be. Normally, the perplexity will be higher than 1. Okay, so that's perfect prediction. So this perplexity is what people actually use when they pre-train. The pre-train is, I believe, always used on perplexity. They just take all the data they have, they keep some test data, and they try to decrease the perplexity. And often it's also used in the post-training, but post-training depends on application. There are other things. But in terms of like, if you're looking for a single measure, probably this is it. And probably there's no other. That's my guess. Like if you look at something will be general that you can say, this is a measure of how well you do. So clearly for specific applications, you can come up like, okay, if you ask questions, what's the fraction of words that you're correct? And other applications will have another one. But if you look at the general measure, that might be the one. Okay, so it's evaluated on several benchmarks. So there's TreeBank, people came up with in 1995, and consists of 1 million words taken from the Wall Street Journal. There's 1 billion words, 2013. Again, and then there's Wikitext, you go with in 2017, and it consists of 103 million words. This here, the articles are shuffled, so it doesn't have the long context that we're looking for. So that's why it's a little less used. And what this is articles from Wikipedia, and they therefore have longer context. Okay, so this one is the most studied and the one we'll use. And just so we see, so it has 103 million words, and the training is 102.6. The validation is 200,000, and the test is another 200,000 from this database. Okay, so people have been working on this database from 2017, quite a few works. So I'll just tell you about some of the popular language models and what they achieve. So the first, maybe the first one that showed good results was adaptive inputs, ADT. And what they did there is they take the neural network and they embed the words. I'll talk about it a little bit in a second. They embed the words in dimensions that is related to the frequency of the word. That's what it's called adaptive inputs. And that achieved perplexity of 18.66. So after every word, they can predict it's on average, one of 18 words. Pretty good. And then, so this is 2019. In 2020, people came up with KNN, K nearest neighbors. And what that added to this is they look at the words that follow similar context. So looking at the current context, they looked in the past, see similar context, they'll see what predicted it, and they make a prediction based on that. So that helps in, so if you just use that by itself, then you cannot do it, because they just look at the 1,000 previous words, and often there'll be words they have not seen. So the way it's usually used is being combined with ADT. And that helps in many other estimators. Then there's short former, which modifies the transfer. Short former is for transformer, modifies the transformer somewhat and reduced it to 18.15. And then moving average equipped gated attention, mega, that reduced it to 18.7. That's 2003. Okay, and I think they call moving average equipped, which doesn't make sense. It made more sense to call them just moving average gated attention, but I think they prefer this acronym to the other acronym. So, so what I want to do now is just see how perplexity is related. So I want to move to equivalence. I want to relate perplexity to information theory. Okay, so just relate them. Okay, so actually it goes back to Shannon, and it goes back originally to the same mathematical theory of communication paper that he wrote. And in it, if you look at section 3, he was actually doing exactly this. He was trying to see if he generated sentences randomly, how realistic would they look? Okay, so here the first thing that he did here was just generated letters according to the right probabilities, and they obviously make no sense. And then this is like a Markov chain, like every word first order, every letter with the right probability given the previous letter, and looks like a little more realistic. And then given the previous 2 letters, then you can see now you're getting almost real words. So even then there was a hallucination, like astronames instead of astronauts, but almost real. And so this related to every word, every letter given the previous two letters. And then he moved from letters to words. So this is words generated independently, and here words that are generated given the previous word. Okay, and you can see that actually, if you just generate words randomly, given the previous 2 words with the right probability, then it almost looks realistic, right? I mean, you can read this. It's a little hard for me to read. So almost looks real. And when you see that the previous 2 words, you can get something that looks almost real. That gives you a lot of hope to see what we are seeing now. Like it's like a little less surprising that we can do well if this is what was done in 1948, just given the previous 2 words. Okay. All right. Okay. So what's the connection? So perplexity is essentially the same as cross entropy. So perplexity, as we said, is and entropy, of course, was the concept that he defined. So perplexity, as we said, is one over the probability of the whole sequence, which is the geometric average of one of the probability predictions. If we take log of perplexity, log of that, we'll get 1 over n, summation of log of 1 over the probability of wi given wi minus 1. Now, maybe we can ignore this, but we can see, like, if we think of, we try to estimate. Imagine that you have IID, it will also hold it in non-IID. Then how many, so every time we'll look at the number of times that we'll get word I in the long text is going to be the probability, the actual probability of the word I. Okay? So this will converge to summation of pi times log of 1 over qi. Right? Because if we just look at this, How many times will I with WI? Probability, the actual P of WI. Summation of PI minus log of 1 over QI is very similar to summation PI log of 1 over PI. This is called cross log of 1 over the expectation. So essentially, perplexity is the exponent of the cross entropy. So it's essentially the same quantity. Okay. Sorry about that. Okay. So and that's a quantity that's being used in information theory, because in information theory, we know that as we said, we can achieve the perfect compression. But to achieve the perfect compression, you need to know the probability. You need to know which probability is more likely, give a short description, which probability is less likely, give it a longer description. And the probability is typically not known. So people do what's called universal compression, okay, which for memory sources says you have a distribution P, which is an ideal distribution of k-simples, and its entropy is h of p, and you can show that the entropy is always less than log k. So if I have a distribution of k-symbols, I can describe each symbol most log k bits, okay, and typically this entropy will be a lot less than log k, a lot less than this log k. Okay, so if you want to compress sample from p, then if p is unknown and you use just one sample, then you need h of p. That's the original meaning of entropy. If you have n samples, then you need n times h of p. That's when p is known, because the entropy increases linearly. If p is unknown, okay, then if you have one sample, there's nothing you can do. Don't know anything about distribution. You need log of k bits. But as n increases, you need n times h of p, which is the number that you need if you knew the distribution, plus k minus 1 over 2 times log n. This is the extra term that you get for not knowing the distribution, and reflects how quickly you can learn the distribution. And we define the redundancy to be the number of bits above the entropy that you need to compress when you don't know the distribution. It's this extra term here. Okay, so extra number of bits beyond entropy, and which is the extra number of bits beyond when p is. So this is when due to not knowing p. Okay, and what we see is that if you look at all n sample, if all the samples compressing them, so we get here k minus 1 over 2 times log n. And if we normalize it to per sample, we see that it's k minus 1 over 2 times log n over n. So it goes to 0. So even if you don't know the distribution, you can compress the sequence essentially as well as if you know the distribution. Instead of h, you'll have h plus this number that goes to 0. We're good? Okay, cool. And goes to infinity, goes to 0. Okay. Now, so you can compress this if you knew the distribution. It's good. Okay, now if you have a source with memory, then you can apply the same results, just extend them. And so you can see, for example, that if you have a Markov source, then you want to learn the distribution following each context. Given this context, what is the distribution after that? Okay, and so what is the redundancy going to be? You have S states. I wrote someplace. You have S states, and for each one, you'll have the redundancy goes to 0. So total redundancy is going to be S times 0. And I guess as the n goes to infinity, the redundancy will go to 0, because you learn the distribution in each context. So eventually, by the previous results, after each context is IID, you learn it, the redundancy goes to 0, multiplied by the S state, still 0. Okay, so that's good. And if you have a stationary ergodic processes, you can show the same thing. So what it means is you can compress this if you knew P in advance. Okay, so this is kind of like the information theory miracle. You can compress without knowing the distribution. Okay, but there is one bad thing here, which is in order for this to happen, and the number of samples that you have, your training size, has to go to infinity for this to hold. Okay. And yeah, this number of states and redundancy of each. Okay, so right. So this slide is not complete, but this is a small plug for previous word. So what happens is that if you look at English, then you have very large vocabulary. For example, for wiki text that we work on, the vocabulary size is 270,000. Okay, so if we have k minus 1 log n over n, then k that you multiply is 270,000. And while you might think that n is very large, but it's not, because n is the number of times that each context appear. And here today people look at contexts that are 512 words long. So so how many times will a context of size 512 appear? Very, very few times. So n is very small. So this redundancy is going to be very high. Remember, we're trying to compete with redundancy that is like 13 point something 4, which is the best that we've seen. So this will be much larger. So this redundancy is going to be very large. It's not very useful. So what we have done is we changed the measure. Right? But we changed the measure from the redundancy to something. Redundancy is you're trying to compete with, in some sense, God. Like God knows entropy. God knows the distribution. You're trying to see how much you need beyond that. But this is about years ago. What we did was said, let's change the measure. Instead of comparing ourselves to God, we're going to compare ourselves to a genie that knows more than we do, but not as much as God. And we showed that compared to the genie, which actually you can achieve diminishing redundancy no matter what the alphabet size is. So that's not what we're discussing today. Okay, right. Okay, so so the way things are done these days is you convert words to vectors. Okay, typically in 1024 dimensional space, and you learn two mappings. One is that you map, so you map the context into a vector in this space, and the other one is you take the words and you map each word into another vector in this space. So every word is converted to a vector, and every context converted to a vector. And given the context, let's call it C, what you do is you take every word in your vocabulary, like the 270,000 words that Wikitext say has, and for each one you calculate the inner product, the vector that represents the context times the vector that represents the word. Okay, call it RW, and then you calculate what's called the soft max, which is these are embeddings and functions. So, and which is just normalizes this. You take each RW, exponentiate it, and you want to make it into a distribution, so you divide by the sum. Okay. So that's how you predict the next word in current systems. Okay, and this will give you a vector Q bar. So what you can do is you can let R be the collection of all this products for all words, and Q bar be the collection of all predictions for all words. And we can write this in short as saying that Q bar, this Q vector, is the softmax of the R vector. This is what it means. Okay, all right. Okay, and so you can think of like the RWs as unnormalized log probabilities, then the Qs as the probabilities. Okay, right. Okay, so let's skip this. There are so we're going to discuss two types of adapting. Like what we're saying is we're taking this and we're going to just modify them slightly, and some of them somewhat based on information theory motivations that we'll discuss. And we have done some more. I'm showing you like a subset of what we've done. Okay, so so the two types of adaptations that we'll do is one of them is improving the estimator, and the other one is taking an ensemble of different estimators. Okay. We'll talk about this. Sorry about it. Okay, sorry. Okay, so let's do this. Okay, so just give me 1 second. Yeah, okay. All right, so this has been a little simple. So what we'll do now is we're going to turn up the heat a little bit. So So in some applications, and specifically when people do calibration or when people do text generation, they post-tune the models, okay? So remember that what we have done before was we took the inner product and calculated RW to be the inner product of the word vector and the context vector. And this is the unnormalized log probability, okay? The people call it logit. And then what they did was they make this mapping a little richer. They divided it by a temperature parameter, tau, okay? So RW, instead of using RW in the exponentiation, they used RW divided by tau. Okay, so now the estimated probability is the exponent of RW divided by, before it was the exponent of RW divided by the sum, by normalization. Now is the exponent of RW over tau, okay, divided by the sum, just normalized, okay? And the vector is just is this vector. Before it was the softmax of R. Now it's going to be the softmax of R over tau. So basically just a softmax of a linear function of R. So hopefully that's clear. So the RW is the inner product. Before they just exponentiate that. Now they're exponentiating the RW over tau. Okay, and so this is tau. This is the tau that if a given tau, this is our QW that's written here. The exponent is proportional to the exponent. Okay, and if you look at its as tau increases, this exponents will become more flat, right? Because if I get tau to be very large, then RW over tau is going to go to 0, and there will be no difference between them. So these quantities become more flat. They'll become more flat, and because they become more flat, the randomness increases. Because if you're going to generate text, because each of them will have the same probability, it does not matter which word, they get uniform probability. So the randomness increases. That's the source of the word temperature. And if tau decreases, okay, then these things will become less uniform. Right, because I'm actually tau. Imagine that tau is like close to 0. I'm really extenuating the difference between different RWs. Okay, and therefore the text generation will become smaller because now only given probability to very likely words. Okay, so temperature is high, you get more random. Temperature is low, you get less random. Okay, and so this explains the names. And what we'd be interested in is this quantity here, because it controls the flatness of the distribution. Okay? So and then you can say, okay, if I do that, then I can use also piecewise exponents. Now I'll get to that in a second. So before we looked at instead of PW being e to the RW, we e to the RW, and then you can find the best tau to modify this. Okay, but then you can ask why not if using one exponent, why not use different exponents for different intervals of the range? So you have k intervals, and for each interval you use a different tau, different temperature. Okay, and you multiply them so that you'll get a continuous curve. Okay, and if you do that, then you see that, for example, for ADT, so when you evaluate things, and then you get 18.66, and this is the original one that we saw. If you find the best temperature, you can actually this one, it will not make a difference because the neural net can already account for this. But if you take piecewise, it reduces it to 18.44. Okay, and if you look at another estimator mega that we mentioned, then originally it's 18.07. It reduces to 7.58 and then 17.44. Okay, and these people, they did something which is related to that, but not the way we're doing it, and also not like as a post-training. But this shows you that this post-training works. Okay, and if you look at short former, again, this reduces the perplexity. So the next thing you can try is look at ensemble. So you have different estimators, like we mentioned a few, and you can combine different models, okay? And you can try to combine them by a linear ensemble. So the static weights. So give one model some probability, 20%, another one 30%. Or you can do adaptive weights that are related to some features of the distribution. And you can also look at non-linear ensembles. So that's what I'm going to talk about now. Okay. So first, let's talk about the fixed weight. Let's talk about weights that depend, the probability depends on the distribution. Okay. So suppose I tell you, I have two models, Q1 and Q2. Q1 gives me this probability, 20%, 40%, 30%, and 10%. And Q2 gives me these probabilities. Now I'm going to assign a weight alpha 1 and alpha 2 to these two distributions. So they sum to 1. And I'll get the ensemble, which is alpha 1 Q1 plus alpha 2 Q2. So a natural question to ask is, if I don't give you any more information, I just give you the output of this estimator, the output of the other estimator. So use two estimators, and I want to create this. What should alpha 1 and alpha 2 be? And these are Q1 and Q2. What would you say they should be? So that's obviously a tough question to answer right away. So let's make it the question a little easier, and just say which one should have a higher value. Which one should we give a higher weight? This estimator or this estimator? Okay. I'll give you a hint. And actually, the hint contains a hint. And the hint is that what this arrow points to, which is H. Okay. So H, as we saw, is entropy. Okay. So we can use the entropy to see which estimator should get more weight. And is it far-fetched to use entropy? Probably not, because H has been actually used in some distribution estimation, so it can come in. Okay. So the question remains, which of those should we give higher probability to? Okay. If we want to use entropy. So I'm going, who has heard of the maximum entropy principle? Okay. So there's something called maximum entropy principle. It goes back, I don't know, 50, 60 years, or 70 years. And it's due to Jaynes, and says that of all distributions of a given state, and a given state means that satisfy a given constraint. So you look at all distributions, you take samples, and you see that the average is 10. Question is, which distribution should you assume? So they satisfy certain constraints, and which distribution of the many distributions that have this feature, this expected value, which one should you choose? And it says that of all distributions that satisfy certain constraint, the most representative is the one with highest entropy, well-known principle. Okay, so if you ask yourself, why would you do that? Why would you use the distribution that has the highest entropy? And so you can see that it's the least committal. Okay, so for example, suppose I know nothing. I'm trying to estimate the distribution of a coin, or not a coin, let's say a die. There's 6 values. I know nothing. So what would we assume that the distribution is? Uniform, right? We'll never assume that the probability of 4 is 1, for example, right? Without saying, we assume uniform. And why? So in other words, we're choosing the distribution with the highest entropy. Why do we do that? One explanation is there are more high entropy distribution than low entropy distributions. For example, if we look at all the molecules here and ask what's the distribution, very small chance that they'll all concentrate in one location. Most likely every molecule is someplace else. So more likely spread out, and the higher entropy. And that's because there are more such distributions. So there are more ways to arrange them all random points and so on. So it's high entropy is more likely. Okay, and that's also the same as the second law of thermodynamics. Okay, so that's the high. that's the maximum entropy principle. Okay. And so what we want to do is we want to use entropy as an ensemble parameter. So what we do is we use a feed-forward network that we feed to it the entropy of the one estimator in this case, and the entropy of the second estimator. And with it, we find alpha such that alpha times Q1 plus alpha bar Q2 minimizes the perplexity over the validation data. So that's what we do. And then we evaluate this new estimator Q over the test data. So when you take KNN plus ADT, these are the two estimators that we mentioned, then you can see that, and we use the adaptive temperature. So we talked about before and about improving this estimator using adaptive temperature. So we do use that. Okay. So with static weights, you see that the perplexity that you get is 15.82. And if you use entropy, you get 15.12. Okay. And then you can ask, okay, so let's see what's the relationship between the entropy of the estimator and the weight. Okay. So this is, we're looking at ADT and KNN, these two estimators. Okay. And here, this shows the weight that we give, this shows the weight that you give KNN, and this shows the weight that you give ADT. And the yellow means that you give ADT a high weight. And what we see is that if you say take a straight line here, you see that the lower the entropy, the higher weight that you give ADT. And likewise here, if you look at KNN, you see that the lower the entropy of KNN, the higher the weight that you give. So it's here that you give lower weight to blue is low. You give lower weight to ADT, therefore you give higher weight to KNN. Okay. So how do we explain this? So it's the opposite of what we expected, right? I mean, if we take ADT, for example, if we look at lower entropy, like here, okay, we give it, just a second. So when you look at, so if we take, this is the entropy of ADT. If I look at low values, okay, then I get this. Actually, I think this image is wrong, but it's reversed. When you look at low entropy of ADT, we actually give it low. I'm sorry. Yeah, when we look at low values of entropy, we give it a higher weight. If we look at high value of the entropy, we give it lower weights, which is the opposite of the maximum entropy. Maximum entropy should tell us that when the entropy is higher, we should give it higher weight. And here we give it actually lower weight. And the same for KNN. If you look at KNN with high entropy, we give it we give it lower weight, right? Because ADT higher weight and KNN give lower weight. Okay. So we see that we see two things. First of all, we see that ADT get in general higher weight, and that's because it's a better estimator by itself. And then we see that lower entropy implies higher weight, which is the opposite of what we thought. Okay, so the question is, why we give a higher weight to low entropy? So the question, does that contradict maximum entropy? And the answer is no, it actually agrees with it. Okay, because maximum entropy says that you should use the estimator should, if you take an estimator, the estimator should choose a consistent distribution consistent with what we have, that has the highest entropy. Okay, and here what we do is what happens is something different. We're given two estimators. Okay, and both of them we know compress well. Both of them are actually very good estimators, were the best at the time they were introduced. Okay, both of them compress well, and they do a good job, right? They're good estimators. So when you have a lower entropy estimator, okay, that means that it's more confident. That means that in some sense it's based on more data. Okay, and so because if it wasn't so confident, then according to this principle, it would give higher entropy. So the fact that it gives lower entropy shows that it's more confident about the collection of distributions. And so we therefore give higher weight. So lower entropy estimator means it's more confident. Okay, and therefore we give it higher weight. Another way to see, so give low entropy estimators higher weight. Another way to see it is to look at Occam's razor. So if you, that says that the simplest explanation is the best. And so that's another way to, another interpretation. Good. Okay, and when you combine, if this is combining two estimators, if you combine all four estimators, then that we mentioned, ADT, KNN, Mega, and short former, then with static weights, you get 13.75, and when you add the piecewise exponential, the piecewise temperatures, then goes down to 13.61. The rest are adaptive combinations. So these are static combinations, fixed like 20% one, 20% this one, maybe 30% this one, so on. And then if you look at the adaptive combinations and we use the entropy, and we also use something called minimum distance that I skipped. Then here you get 13.01, and this is just using minimum distance that I skipped, and this is using entropy. And when we use both, you get 12.81. Okay, and you calculate here the weights using a feed-forward network. But all these are linear estimators, combinations. And the next thing to ask is, should we use the linear combination? So what you can do is you can look here at the probability of the next word as a function of the prediction of two estimators like the ADT and KNN. And as you can see, this is not a linear combination. There's no, if you take a straight line here, there will not be a fixed value. If it's a linear combination, then there should be a line here that would have the same value. Like, for example, I took, just added them up, then this line, the diagonal here, should have the same value. Okay, but there's no such line. So that suggests, and this is a somewhat modified picture of the actual one. Okay, so it suggests that you should look at nonlinear ensembles. Okay, so linear is Q is summation alpha I QI, and this is guaranteed to be a distribution. Nonlinear, you can look at Q, which is a function of some arbitrary function of the distributions, and you can learn it by a feed-forward network. Okay, notice that this now is not a distribution, like this is not guaranteed to be a distribution, so we need to just normalize the values, not so important. And then the improvement that you get from that is, so we're using piecewise exponential that we described. We're using entropy and minimum distance, okay? And these are the values that we get. So if you look just two estimators, ADT and KNN, you get 1509 and 14.91. If you use all four estimators, you get 12.81 and 12.74. And just to show you that this method works well, here you see the actual values, so the actual predictors of KNN and ADT. And here are the actual accuracy. And this is what we get with this method that we are applying, that we're using. So the accuracy that we get is very similar to the actual accuracy that we see of the next words. So this is the fraction of elements in the bin that were actually appeared, and this is what we predicted. Okay, so then when you combine everything, okay, and there's a paper by so this ensemble is a known technique. So there's a paper by Errol Mikov. Mikov is, by the way, the guy who came up with the word vec, this mapping that you map words to vectors. Okay, and so these are the results that we get. So their results was 13.29, which is the record until now. And by using what we've said, you get 12.39. So if we put it back on the leaderboard, so these were the results that people had. And you can see, for example, if you look at from 20 to 23, it was reduced from 15.79 to 13.29, so by 2 point something. It's not a huge reduction. And if you add the results that we have now, so you get 12.39, so it's 0.9 reduction. So not super dramatic, but in the line of what was done before. Okay, so to summarize, Um, so we talked about perplexity, which is a fundamental concept that is central to LLM. One would argue if you were looking for one concept, one that can be measured and is used across the board, and makes sense, then maybe it's the only one, and also applies to applications. And we saw some simple probabilistic and information-theoretic concepts that help improve. And for model improvement, we did piecewise temperatures. Okay, and for ensemble, we looked at linear with using entropy, using minimum distance, and also nonlinear. And we showed that we can reduce the perplexity from 13.9 to 12.39. Okay, and so basically that's it. So I don't think that we're putting information theory in front of AI, but hopefully we're helping it move it slightly forward. Thank you. No, well, because so if you have a model so the way this thing, you train the model and then the model and then you test it like the Google, you test it like all the essentially all the if your model always predicts the same word and the most popular ones, probability that this model will give because every time you have D, every time you multiply, okay, the inverse of that is the testing.
How do I know? Why did I pick? Think intuitive. Lower temperature.
So wait. Those
Piecewise thing.
okay, we'll get to the piece. They will shrink. Yeah, exactly. I think a lot. I speak to. But you should move $1 billion.
All of them were dating around 1870. About like and also like how different should just take ADT and ADT and ADT.
Yeah, okay. Yeah, well, it's just two separate questions, but both very good questions. Let's start with the second one. So if you did ADT and ADT, just let's say twice, okay, you'd think you shouldn't get an improvement, but you might. Because there's all these things have a lot of randomness. So like the mapping that you have, like all these things that we talked about, the mapping for the context, all of this is random. So if you do it twice, you get two independent views, and getting two is like flipping a coin twice. You'll get a better estimate, right? I mean, if you
just to clarify, it's not the same copy of the ADT model.
No, you could. No. So yes, so if your question was if you use the exact same ADT, then of course you will not, because linear combination of the same value will give you the same value. But you could train two ADT. I'm just want to say, even if you just did ADT the same method, but just train it twice, you might get better results. So that's for that. Now the second, both of you asking questions that are asked very politely, but have a slight of challenge in them. So I'm not sure if everyone knew it, but one could. So it's in a slide that I skipped. So we're taking two estimates and combining them. And maybe one could argue that that's not fair, like because they're using one model and we're using two models, so and we're getting improvement, right? So first of all, we're comparing ourselves to another approach by people of the well-known person in this field that also combine them, and we get improvement. And the other issue is, or several other things, our goal is to see what's the best way, information theory, what's the best that's possible. So you don't, even if we're using more parameters than what each one, that's important. But for us, we first want to see how low one could get and then maybe improve it. So that's the second part. Third part is there's a lot of work on, not a lot, but there's a fair amount of work on trying to take models like this and reducing them to a smaller model. Because once you have a model, larger model that can predict things, then you can use it like as a teacher to you get samples, see what the model says, and you can train. That's another approach that one could take. We haven't done it, but I should mention, since this reminds me, that we only looked at this. If you look at this leaderboard, sorry, here. So here you can see, so you see model using, not using extra chain. So all these are trained just on Wikipedia. You can also take, if you're Google, then you can train it on all the data in the world. And they have done that. When you do that, the perplexity reduces dramatically. So, but this is considered to be an unfair comparison, because they might be using Wikipedia in German. And then they figured out, they write it. They're trying to avoid things, but they write in the paper themselves that they write that this exists. So just because you mentioned this issue, if you're going to use external data, then you can get much lower complexity.
Thanks, Alon, again. And thank you all for